Of course, not all signals are sinusoids. Signals have general spectra. But if they are not band limited and they are sampled, the out-of-band spectrum will fold back exactly in an aliased manner as we have seen with sinusoids. Of course, this is a nasty phenomenon because then the spectrum that we see in the baseband does not correspond to the proper spectrum of the signal, and so this has to be avoided. What you have to do is you have to apply low-pass filtering, namely a low-pass filter that cuts off frequencies beyond half of the sampling frequency, and then we can properly sample a signal. This is what we're going to see in this module. Module 6.5, Sampling and Aliasing. We have seen aliasing for very particular signals, sinusoid complex exponentials. Now we're going to look at aliasing for arbitrary spectra and look at a few examples. We will finish by wrapping up sampling of arbitrary signals using the projection theorem onto the space of band-limited signals. Remember the raw sampling of an arbitrary signal. So you have a continuous time signal xc of t sampled every ts seconds to give a sequence xn, which is equal to the continuous time signals at multiples of the sampling interval ts. In Fourier transform domain, we have a spectra of the continuous time signal, capital X, C, J, capital omega, and at the output we have a discrete time Fourier transform of the sequence, that's capital X e to the j omega. What is that going to be in general? And how is it going to be related to the input spectrum? The key idea is the following. Pick a sampling interval Ts, or a frequency omega n equal to pi over Ts. Start with omega 0, which is smaller than omega n, the Nyquist frequency, which is the maximum frequency that can be faithfully represented with this sampling system. So the input is e to the j omega 0 t, it's sampled with Ts, it gives an output e to the j omega 0 Ts times n, that's the sequence resulting from this sampling operation. Then let's add 2 omega n to the input frequency. So now the frequency is omega 0 plus 2 omega n. It is sampled. At the output, it is omega 0 plus 2 omega n times Ts times n. We expand this product. Then we see that the second term becomes 2 pi n, but 2 pi n raised to the power e to the j is equal to 1, and therefore we have the same discrete time sequence as before. So we do not see this higher frequency complex exponential, it simply looks like the lower frequency exponential omega 0. So in general, if we have two frequencies, A times complex exponential omega 0 plus B times the complex exponential omega 0 plus 2 omega n, sampled, it gives you A plus B e to the j omega 0 tsn, so the upper frequency one has been folded back or aliased back onto the lower frequency one, and we simply see the sum of these two, and so the aliased part has been shifted back to the non-aliased one. So what is the spectrum of a raw sampled signal in general? Well, let's look at the sample xn. It is xc at location nts. We can write this as the inverse Fourier transform of the spectrum capital Xc multiplied by the e to the j omega nts, because that's the location we want to evaluate the inverse Fourier transform. Frequencies that are 2 omega n apart will be aliased. We have seen this specifically on an example just a couple of slides before, so we can split the integration interval into pieces of size 2 omega n, and this we do here. So xn, this inverse Fourier transform, is now the sum of the pieces from 2k minus 1 omega n to 2k plus 1 omega n of the Fourier transform here, and multiplied by the complex exponential at nts. Let's look this on a picture. So everything that is at location 2 omega n will be folded back to the origin. What is at 2 omega n plus epsilon will be folded back to epsilon. What is at 2 omega n minus epsilon gets folded back to minus epsilon. The same symmetrically around minus 2 omega n. The same from 4 omega n and minus 4 omega n, etc., etc. So we can go back to our formula. We do a change of variables so that the integral is between minus omega n and omega n. This changes the frequency variable inside of xc. Then we also note that adding multiples of 2k omega n to the frequency doesn't change the frequency. That's the famous aliasing effect. We can interchange summation and integral to end up with 1 over 2 pi, the integral, the summation of the spectrum xc and its shifts by multiples of 2k omega n. And then at the right end we still have the integration variable for the inverse Fourier transform. Let's define a periodized spectrum. So capital X tilde C is the summation of xc and its shifted versions by even multiples of omega n. Therefore, the sample xn is the integral between minus omega n and omega n of the periodized spectrum x tilde multiplied by e to the j omega n ts. Let's do the following change of variable. Small omega is equal to capital omega times ts. This will change the integration boundaries from minus omega n to omega n into minus pi to pi. It changes the frequency inside the x tilde and it changes the exponent to j omega n, which is more convenient. So we recognize now that xn is the inverse discrete time Fourier transform of 1 over ts, this periodized spectrum x tilde c rescaled by ts. An important point to note is that this periodized spectrum rescaled is actually 2 pi periodic, so it's a valid DTFT. Since this is the IDTFT, it means that the DTFT of the sequence, capital X of e to the j omega, is simply up to a scale factor of 1 over ts, the summation of xc and its shifts by multiples of 2 pi over ts. A picture is worth 1,000 equations, maybe. So let us look at the spectrum and how it evolves. So we start with capital XC. It's a spectrum which is inside the boundary minus omega n to omega n, doesn't cover the entire interval. Then the periodized version puts repetition spectra at 2 omega n, 4 omega n, etc. This is now a periodic spectrum of period 2 capital omega n. The spectrum of x of e to the j omega is a scaled version of this. It is 2 pi periodic and it is shown here at the bottom in blue. Let's take a band-limited signal, but it is band-limited to omega 0 equal to omega n. This is the limit of the Nyquist sampling frequency. It will be periodic of period 2 omega n, which is equal to 2 omega 0, so the repetitions will just touch each other. It is therefore the usual periodic spectrum. And now we look at the spectrum of x of e to the j omega. It fills the entire interval minus pi to pi. What happens when omega 0 is bigger than omega n? Well, we know trouble is going to come because aliasing will happen. So we see that the spectrum is beyond the central interval of minus omega n to omega n. So the repetitions will overlap with each other. The result is still 2 omega n periodic spectrum. We see it has a funny shape now. It's not the original shape because of the overlaps. And when we look at the spectrum of x of e to the j omega, the blue spectrum, it indeed does not resemble the original spectrum because an entire interval has been messed up by aliasing. Let us look at the non-band-limited signal. So this is a Gaussian type of signal which has decay but goes well beyond the central interval minus omega n to omega n. It is, after sampling, the periodized version is 2 omega n periodic, of course, but there are overlaps all over. And it has in the center of the interval shapes that resemble the original spectrum, but then it has overlap. And so the blue spectrum, which is between minus pi and pi, resembles the original spectrum around the origin 0, but is different from the original at the boundary of the interval. This leads us to sampling strategies for different signals. So if we are given a sampling period Ts and the Nyquist frequency omega n is equal to pi over Ts, if the signal is band limited to omega n, then raw sampling is fine. It's equivalent to sinc sampling up to a scaling factor. If the signal is not band limited, we have two choices. Either we band limit it first with a low pass filter that will cut off all frequencies beyond omega n in the continuous time domain before we do sampling. Then everything will work just fine, as we have seen. Or we raw sample the signal and we have aliasing. Now, let's face it, aliasing usually sounds horrible, so usually it's not the first choice. So let's investigate a little bit how we sample signals that are not strictly band limited to begin with. So how do we do sinc sampling and interpolation? Well, the sample x hat n is simply the inner product of the sinc function shifted to the location n times ts with x of t, the input signal. This can be written simply as the convolution of the sinc with x at location nts. Then the interpolation x hat of t is the sum of the samples multiplied by the sinc function shifted to the location nts. We see this in this block diagram. From left to right, we have a continuous time signal xt. It goes through an ideal low-pass filter with a cutoff frequency capital omega n. It is sampled every ts seconds. The samples are interpolated by sinc interpolation, and the result is x hat of t. It is interesting to look at this scheme in purely geometrical terms. So we have an input signal x, it's a vector in a Hilbert space. We have the subspace of band-limited signals, BL. The first thing we do is we have an orthonormal basis for BL. It's given by the sinc function and it shifts by integer multiples of capital TS. Based on this orthonormal basis, we write an orthonormal expansion, which is the orthogonal projection of x onto the space of band-limited signal. So it's written as a sum of the sinc inner product with x times the sinc functions. And so we see that the scheme we had on the previous slide is simply the projector of x onto the subspace of band-limited signal. That projection, of course, can be written in terms of the sampling theorem. But we cannot write x, we can only write x hat, the projection. Now let's look at a concrete example, one that we have encountered before, which is a non-band limited signal. Here's this Gaussian-shaped signal, and we're going to do least squares approximation on the space of band-limited signals using sinc sampling and interpolation. So we start with capital XC, the continuous time spectrum, non-band limited. We are going to band limit it to minus omega n to omega n. This is given by this green ideal filter. After filtering, the spectrum is strictly band limited. It's zero outside this interval of size 2 omega n. Then we do the sampling, and this leads to a periodic spectrum x tilde c, given in this pink shape here, and it repeats at multiples of 2 omega n, as we have seen before. Then we look at the DTFT of this sequence, and the DTFT is 2 pi periodic. It's given by this blue function. And finally, we reinterpolate a continuous time spectrum using sinc interpolation that gives us x hat c, which now is exactly the reconstruction of the band-limited version of the initial xc. This band-limited version, of course, is the orthogonal projection of the initial spectrum onto the space of band-limited signals.